Hello everyone, welcome back. Today, we are diving deep into two critical electronic effects that govern how organic molecules behave. While the inductive effect is like a permanent pull, the effects we're discussing today is hyperconjugation and the electromeric effect. They have their own unique rules. One is a permanent, Baker-Nathan, miracle, and the other is a temporary, on-demand, reaction. Let's break them down step by step. Hyperconjugation is the delocalization of sigma electrons specifically from a CH bond of an alkyl group. This happens when that alkyl group is attached to an unsaturated system like a double bond. And if it attached to a carbon with an empty p orbital, like a carbocation, the sigma electrons from the CH bond start to spread out into the nearby system. This spreading is called delocalization. Think of it like sharing pressure instead of one atom holding all the charge. Nearby bonds help distribute it. So remember, hyperconjugation equals sigma electron delocalization from CH bonds to stabilize a nearby double bond or carbocation. That's why molecules with more alkyl groups are more stable, because they show more hyperconjugation. Why do some molecules become extra stable just because of nearby hydrogens? Let's unlock the conditions behind hyperconjugation. To understand hyperconjugation properly, you must know its two key conditions. First, the alpha carbon. You must have an sp³ hybridized carbon directly attached to an sp² carbon. In simple words, a single bonded carbon next to a double bond, or next to a carbocation. This setup allows the sigma electrons to interact with the adjacent system. Second, alpha hydrogens. The more alpha hydrogens you have, the more hyperconjugative structures you can draw. And that means greater stability. Think of each alpha hydrogen as a helper. More helpers means the load gets distributed better. Always remember this rule. More alpha hydrogens means more hyperconjugation, which means more stability. In exams like GPAT, stability questions are very common, so pay close attention. Here's the golden rule. More alpha hydrogens means more stability. Now let's apply this. For carbocations, the stability order is: tertiary is more stable than secondary, secondary is more stable than primary, and primary is more stable than methyl. The reason is simple: tertiary carbocations have the maximum number of alpha hydrogens, so they show maximum hyperconjugation. Now let's talk about alkenes. Substituted alkenes are more stable than terminal alkenes. Why? Because more alkyl groups mean more alpha hydrogens, and that leads to greater hyperconjugation and higher stability. So just remember, count the alpha hydrogens, and you can easily predict stability. Let's understand the electromeric effect in the simplest way possible. The electromeric effect is a temporary effect seen in molecules that have multiple bonds, like double or triple bonds. Now here's the definition. It involves the complete transfer of a shared pair of pi electrons from a multiple bond to one of the bonded atoms, but only when an attacking reagent comes close. Right finger in simple words, when a reagent attacks, the pi electrons shift completely to one side. And here's the most important part, this effect is reversible. That means, as soon as the attacking reagent is removed, the electrons go back to their original position, and the molecule returns to its normal state. Blank, underscore, blank. Bullseye. Easy way to remember, electromeric effect equals temporary plus complete shifting of pi electrons plus only during attack. Now let's talk about the types of electromeric effect, super important and very easy if you get the logic. There are two types you need to know, plus E effect and E effect. Let's start with the plus E effect. In this case, the pi electrons shift towards the atom where the reagent is going to attach. So basically, electrons move in the same direction as the incoming reagent. A simple example is the addition of a proton to an alkene. When the H approaches, the pi electrons shift toward the carbon that bonds with the proton. Right finger. Easy way to remember, plus E means electrons go with the attacking reagent. Blank, underscore, blank. Now let's move to the E effect. Here, the pi electrons shift away from the atom where the reagent attaches. So electrons move in the opposite direction of the incoming reagent. A common example is the addition of Cn to a carbonyl group. When Cn attacks the carbon, the pi electrons shift toward the oxygen, not toward the attacking species. Here is the right finger memory trick. E means electrons go against the attacking reagent. Let's quickly understand the difference between hyperconjugation and the electromeric effect, one of the most confusing comparisons in organic chemistry. First, let's talk about their nature. Hyperconjugation is a permanent effect. That means it is always present in the molecule. On the other hand, the electromeric effect is temporary. It only appears when a reagent attacks the molecule. Now, what about the electrons involved? In hyperconjugation, we deal with sigma electrons, specifically from CH bonds. But in the electromeric effect, pi electrons are involved, typically from double or triple bonds. Next is the requirement. For hyperconjugation to happen, we need alpha hydrogen atoms attached to the carbon next to a double bond or carbocation. In contrast, the electromeric effect requires an attacking reagent. No reagent, no effect. Finally, let's look at the result. Hyperconjugation leads to stability of the molecule. This is why more substituted carbocations are more stable. Whereas the electromeric effect causes polarization, helping the molecule undergo a chemical reaction. So in short, hyperconjugation stabilizes, while the electromeric effect prepares the molecule for reaction. That's the key difference you need to remember. If you found this helpful for your pharmacy exams or chemistry basics, please hit the like button. Thank you. Happy learning.